get started. All right, so what we'd like to do is kind of cover the material that's up here on the banners while it's still daylight in here, and we can see what's going on. And I want to talk a little bit about the science behind fluorescence and kind of how it got started, who really kind of discovered it. We'll be talking about ultraviolet light and different wavelengths of ultraviolet light. And this is an electromagnetic spectrum that is, from radio waves all the way to the gamma ray burst coming out of a supernova sun blowing up. You don't want to be in front of one of those, it can fry you. So our rainbow is sitting about in the middle, the sunlight coming out, and you get a prism, you get all the colors of the rainbow. Same thing that happens when the rain shines through the little rain droplets, breaks it up, and you see the rainbow. To the right of that, and I should mention that energy is increasing as I go from left to right. So radio waves, yeah, your cell phones pick up the energy, but there is a whole lot of energy in a gamma ray. I mean, it just blasts everything. So we're putting ultraviolet light on these rocks, and that's energy going into these rocks. And to the right of the visible spectrum are 3 different wavelengths that are available in the market today. We have short and long on our hanging up on these poles here. The long wave stuff is down there, the short wave stuff is down here on the table. So these two, this green one and red, blue one, are the short wave. One in the middle, we can go back and forth. So you're going to see rocks fluoresce with different wavelengths. Again, that's the energy. As we put more energy on, there's going to be more light. Okay, so color, we see color today. That red shirt, for example, is reflected light. The color coming off of these rocks is going to be emitted light. The dyes in your shirt absorb all the colors of the rainbow except the one that, like that red one, is reflecting the red light. The chlorophyll in the green leaves to the spring, then they turn brown in the summer because the chlorophyll disappears and it's reflecting the brown stuff in the rock, or in the leaves. So that's about color. Luminescence is created by cold light, not heat from the sun, but through cold processes. And so basically everything that is on this table luminesces, if you will, and it's also fluoresces. So the words kind of go interchangeably, if you will. The word fluorescent was coined by a gentleman that discovered the principle back in 1862. This guy here is George Stokes. And he was looking at a piece of mineral, like this rock here, and this is fluorite. And fluorite will fluoresce, but he didn't know it fluoresced. He just saw when he had a light tube going down from the sun, and it blocked most of the visible light, and this rock was down at the base of that light tube. He saw something that looked like this, blue. So this blue is from the fluorite. He says, gosh, this rock looks different. It's fluorite. And then he said, I'm going to call that principle where it emits luminescence, fluorescence. Fluorescence from the word fluorite. So that's how we get the word fluorescence, is from this mineral, fluorite. And George Stokes was the one that did that back in 1862. So that's how we get the name. Now, why does it happen? Why does that fluorescence take place? It's all about the energy emitted on these rocks. And that energy is happening on atoms that are in this rock. Now, the atom has a nucleus, has electron shells. It was orbits back when I was going to school, now they're called shells. But what we're doing is putting energy with a light, like one of these light bulbs, on the electrons that are impacted inside these minerals. That electron gets excited, it absorbs the energy and goes to a higher energy state. That's called ionization. Now, they are very unstable out here. They don't like to stay out there. They like to go back to their grounded state. But they have to release the energy that they absorbed from the UV light. It's kind of like when you take kids out for candy and Halloween and they suck in all the candy, and all of a sudden they get all excited, and it takes a while for them to calm down. Same kind of principle. Put energy, get the electrons excited, and then they have to go back, they want to go back to their grounded state, and that's when they release energy in the form of visible light. The principle is they absorb the shortwave energy and release longwave energy in the form of the rainbow. So all of these rocks on the table here, and fossils and petrified wood, will glow a different color based on the composition of the atoms and the electrons that are in these rocks. So that's kind of how it works. Now, the fluorite that I shared, that George Stokes used, is calcium fluoride. Calcium fluoride is the main ingredient in fluorite, but there's another element on the periodic table, a rare earth element, and that's europium. So small, very, very small percentages, upwards of 0.01% to like less than 3% of those impurities are activators that help cause the fluorescence or luminescence activity. If you have more of this europium in the rock, like 4 or 5%, so not all fluorite will fluoresce because it may have too much of the activator. Or it may have copper or iron impurities in it, which dampen the effect. So you say, well, I'm gonna go buy some fluorite, put my UV light on it, and it fluoresces. That's because either it had some damaging effects, or it had too much of the rare earth elements in it in the activators. Or not at all, none present. So that's kind of the basic principle. And then we have some minerals up here with what we call timberescence. Hopefully we can demonstrate that today. It's a unique principle where the rock will change color and then hold its different color with the absence of the light. And then there's triboluminescence. We're going to demonstrate triboluminescence today by rubbing some rocks together. And we're going to create luminescence or fluorescence with mechanical energy instead of UV light energy. So and then there's other applications of fluorescence that you can use to sanitize hospitals, and trace oil leaks, and all kinds of stuff. So UV lights are pretty practical besides showing off rocks.
And they're finally starting to get kind of, usually this stuff gets pricier and pricier, and it is still kind of expensive. This lamp here, I believe that was $1,500 for long wave. They're selling the new short waves now for $2,000. Ouch. Bob's got a handheld there.
Short
battery pack. Those are over $650 now. But we've been working on these LED lights for a long time, and I've never been a fan because they didn't give off the same color. And they were only working with long wave. There is a new short wave out. Last year there was one introduced. He was selling them for quite a bit of money. They were overheating, and somebody was already copying the product by the time we got it to market. So they're in suit, don't know what happened with that. I don't believe it's on the market, but there was another gentleman here in the last show that says, oh, you can get these shortwave lamps now for $130. That's half of what Way Too Cool is selling for. So these things,
We should talk about filters.
Filters.
So besides the ultraviolet light emitting diode that are in here, or in this case the fluorescent tubes that are emitting ultraviolet light, the critical thing is you don't want white light, like these light bulbs shining on the rock. You want to filter that out. So a lot of these products have filters in them. You've got to be careful when you're buying an LED lamp. Make sure they have the filter that blocks the white light and only transmits the ultraviolet light. Otherwise, you'll just be like putting a flashlight on and flashing the rocks.
I've got a great example of the difference of this. If you've ever been out in the desert and looked out at the night sky, there's not way off in the horizon you can see a glow from the city, right? But you look up at the stars and where'd all that come from? Because you're at home, you can't see them, right? You see a couple of the brightest ones, you go out in the desert. It's covered, they're everywhere, there's millions of stars. That's because of white ambient light. It drowns out the color from those stars. So that's what the filter does.
Right, and then also, when we go through this demonstration, you know, we have these different wavelengths, and I said there's 3 of them. We only are demonstrating with long wave and short wave. Short wave is down at this end of the table, long wave is down at this, that end of the table. And so, and their frequency wavelengths are in here. So we're doing that. Oh, we're gonna do we do this once a year in our little kind of skit. We don't have a very solid outline of what they talk about. So there's some cool little demonstrations of sunscreen and a few other things that we forgot to do in the last show.
All right.
So, well, let's get ready for the lights to go out here.
Yeah, it's gonna get really dark. We left one light on. You might be able to see a glow from something over there on the side of the panel. I'll get over that way. It's from a one gentleman brought it in. It's called a Tibetan cave lamp. So this is man-made. I'm sure it's got phosphorus in it, and they've designed it in such a way that it holds its glow forever. We've got one other piece down on the end that lasts for about a minute. Nothing comes close to this.
I can't see it from here. Did you charge it up? Charge that sucker up.
Charge it up. That would take some courage.
You got your light?
Yeah, I just gotta find it in the dark. There it is. All right. Long one. Yay. All right. Charge it up.
There we go.
All right.
Yeah.
I can see it when I turn the lights on. And on the other side, it hasn't got the light. It's still just glowing just a little bit. So it takes that charge and holds it on to it forever.
That's good.
All right. We're going to give you an example here of triboluminescence. I got to hide this guy because it's so bright. This is where you take rub 2 pieces of calcite together. So imagine 100 or 200 years ago or more, where a shaman, a Native American spiritual leader of the community, might be people come to him and ask him to pray for rain. So he would use a tool. It's called a lightning stone. He rub 2 pieces of calcite together and do it like that.
And I have it here too. Can you see it?
After a while, it starts giving off a sulfur smell. So this is from my grandfather's collection. I have no idea how he got them. They're labeled lightning stones.
I found my Moala River crystal, my crystal in the river, Moala River.
All right, this is something new I haven't done before, and I do a lot of quartz, and I've been looking and looking and looking, finding quartz. Quartz by itself is silica, and it's crystals. It's very clear, but you put impurities into it, and you can get all kinds of things. We have this octahedron fluorite that's got little tiny particles of calcite in it. If you look at it, you look like you're looking into a galaxy covered with stars. This is, Chinese are getting really good at this. They're making quartz. This is a petroleum in quartz. If you were to look at it to buy something that happened naturally, this is from Pakistan. So a little petroleum inside the quartz. All right, I'm going to turn on the lights here. We're going to start off with a long wave.
You said confidently. Did you unplug the?
There. All right. So the colors here, you got everything in the rainbow, but this is not reflected. It's creating or generating light. The most brilliant thing down here, that we had a couple guys walk in here one day, same day, 2 different times. Guys walk in here with Geiger counters, and there's a couple pieces down there that are going, not too bad. It's down to this, you're all right. No gamma waves. So as long as you don't eat on it, put it under your pillow, you're okay. So that comes from Spokane Mountain. People are out there skiing on this stuff.
Oxygen.
Yeah. Right. There's a lot of petrified wood, and most fluorescent shows that you go to, people aren't really, they're into minerals and purity. And the guys that used to do this before, they could actually tell you, they were into purity so well, they could tell you the color that was emitted by the wavelength of the light, where it came from. I just love the colors and the textures and just the gorgeous stuff. That orange stuff on there is calcite. There's a lot of calcite. If some of you have white t-shirts on, maybe some white socks, you may see it glowing. It's because calcium is commonly used as a dye. And that was the premise that was used with posters back in the 70s. They would take dye that was fluorescent for posters. All right. Your bones in your body make calcium. So when my son had his teeth extracted, those are the fluorescents. And I'm a fossil hound. I was out in South Dakota in what's called the Badlands, but outside of the Badlands there is some private property, and some of the ranchers will allow you to go out and collect. This is a rhinoceros jaw. So this is the rhinoceros teeth. These are about 40 million years old, are fluorescent. Back when we had rhinoceros on the planet, over on North America. So calcium moves in a lot of different ways. If you all know about plate tectonics, that's earthquakes and the plates are moving. Well, that movement can cause cracks in the earth, and over time, water percolating from above, bringing minerals that are soluble in the water down in, can fill the cracks. There's a friend of mine who gave this to me. He was just very excited to show it to me. I couldn't wait. I said, how brilliant is that? This is called a cowrie shell. And there are poisons. They have a thing that's called a radula that kills their prey. They can't chase you. They are snails. There's some calcium in this. This is a petrified wood that comes from what's called the blue forest. If you were to look at this in white light, all that cream-colored material is blue agate, gorgeous blue. That blue was previously the bark on a tree that fell into water. The brown stuff around the outside was algae that was growing on that dead tree. And then, about 40 million years ago too, did you all know that Prineville is an extinct volcano? It was blowing its top for a total of 40 million years. It's getting all the way over into central northwest. Right? So you can actually tell from where the algae is growing on this, the direction of the blast. So it got hit from this side from the volcano ash, and all the ash over there kind of died, and the algae still growing over on this side from what's on the other side of the tree. And then over time, the bark, it's the cream-colored stuff, kind of dissolved, and then water percolating down through all that ash that covered it, filled in the cracks, and created that fluorescent agate. There's a gentleman that I met down in Sweet Home who was showing me the salmon caves. And he comes out, he's a Native American Indian. He does napping. He's a master napper. So it's kind of, it makes these wolf blades that are over a foot long and obsidian. And then he shows us that tour, opal arrowheads. Now, if you've ever worked with opal, you know that if you put too much heat on it, it explodes in a million pieces. It shatters. But he has a gift for making arrowheads out of opal. So this is a common opal. He was making them from the stuff that comes from Australia, that brilliant fire opal. He made it out of this opalized wood that comes from Virgin Valley. Alright, there's various versions of calcium here. We're going to add a little more color. This is the interesting one. Alright. Some more shells here. I go to the beach and collect fossils. So it's called a trophon shell, and it's fluorescent. You can get regular shells, pretty much hit and miss. Even that cowrie shell I showed you, not all of them are fluorescent. They get some pretty outrageous colors on it. More petrified wood. This one is green. If you've ever seen that redwood that's down from Arizona, the beautiful agatized redwood, this works under short and long wave. I'll have to show that to you again. Various versions of calcite from China, from Peru. fluorite is this different color purple. This is another one that comes from England. These are minerals that come from Pakistan. There's Afghanite and Hackmanite. This is the orange Hackmanite. This is a kunzite. I told you about the petroleum quartz. A new addition to our collection, one of our longtime members, Bee and Fluorescent, who was bee finding passed recently, and we bought her fluorescent collection. So this is a slice of a stalactite. It's illegal to collect stalactites. We've got a couple more examples. There's a gentleman that was a member of the club for, God, since its beginning. He collected for 50 years and pulled a couple stalactites out of his collection. You've ever seen amber? There's an amber necklace. So we've got a ruby necklace down there too. So it's not a high quality amber or ruby, but all of it is fluorescent. There's another version from Indonesia is blue, and amber is a fossilized tree sap. That's the same stuff that they also find insects that, like Jurassic Park is famous for that. Okay? This is a fulgurite, and this may be an example of a heat-related reaction. So this is a lightning bolt fusing sand together. Prior to the impact, the sand was not fluorescent. So there is a heat-related reaction that causes this to fluoresce. So tremolite comes from Quebec. If you've ever been to Eastern Oregon, these minerals here, this is agate, moss agate from Graveyard Point. Oh yeah, showing us. I was at a concert here over in downtown Portland at Minimums, and they were using these LED long wave lamps on the dance floor, and people are dressed in these fluorescent shirts and dresses and clothes. So you could have fluorescent jewelry be the life of the party. This last one here, this is antler. It's antler from an elk. All right. This is petrified wood. It's got a special way that it's formed. They're called limb casts. They come from about 60 miles east of Prineville. This is called Congleton Hollow. And back when Prineville was blowing off quite a bit, it would put ash on the hillsides. And then when it rained, that ash would become a mudslide, taking out all the trees and rocks along with it as it's sliding down the hill. The trees that were crushed and munched up in that were immediately covered so that they could not get oxygen. Therefore, the bacteria could not live, and it died immediately. It is common, though, to find the wood from Congleton Hollow with what's called a trace fossil. Because there was volcanic activity in that area for so long, the wood just wasn't really very happy. So there were a lot of termites in it. So you can get a lot of the wood that comes from that area has termite markings in it. So this is a limb that's been compressed, a little branch, a little twig, and you see that they're all three different colors. And there's another one that's down there that works only under shortwave. And this is all from roughly a 2 square mile area. So you can see that the difference in the trace activators, the amount of the activator, can change the color and the mineral quite a bit. This is a new addition I just found. So the piece isn't terribly fluorescent, but around the edge is part of what's a thunder egg. So there's another example of that. So the blue around the edge is actually oil that penetrated into the matrix around the egg, and you can't get it back out. So the oil that you use to cut your rocks is fluorescent. This is our last long wave lamp, and it's really getting hard to justify in using it because we got these gorgeous high energy lamps, and even our little flashlights are brighter than it is now. Right? So that may have to be our next investment, one that goes shortwave and long wave. My brother was a glass collector, and he gave me a few pieces. So the two glasses in the jar in the end were given to me, and this was found by another glass collector who came out to my house. It was a 1907 Victorian, and back then they didn't have toilets, so they used what's called an outhouse. So outhouse would be built on the farthest corner away from the house on the lot, so that you wouldn't smell it so much, and hopefully it wasn't in the direction of the wind blowing towards the house. So they used it until they filled it up, and then they take everything that wasn't burnable and throw it in the hole. So this glass collector found this lamp out of that. There's a gentleman that used to do this show with us, and he would take these fluorescent handheld lights into glass stores and look for a thing called Vaseline glass, which was made with uranium sands. So you could take your long wave lamp and shine it on the glass, and you wouldn't have to be dark, because this stuff just really stands out, and find fluorescent glass on the shelves. This is a meadowite, some more petrified wood. I'd love to show this puppy. So it's pretty much just white under a long wave, and if you add short wave to it, it gets green. So some of these minerals will work with long wave, some will work as short wave only, and some will work with both. So you see a slight change in some of the colors there, or some new colors that weren't there before. I was goofing around with this one earlier today. I didn't even know it had red in it. So it's blue and a red. And another one that does that is a lot of yellow and green in it. The yellow's brighter. And then you put it in shortwave, and it's got a lot of green in it. So the phosphorescence that we talked about, that's an example of these electrons. When they're returning to their normal states, they return much slower. So this is an example where we've got a long wave, it's one color. If you put it into short wave, it's a different color, and it phosphoresces. So that's the electrons removing back to their normal state very slowly.
We do the same thing with this mineral, which is, never can remember it.
That's terligua, calcite.
And
so that blue is unique to that particular stone from that particular location. Nothing else in the world has that blue color. Pretty sweet. Went to an estate sale from a longtime member who'd been collecting for 50 years. I had to show this one too. I found a piece of coral in there. Right next to it was a stalactite. And I'm a stalactite crazy guy. So I picked up the coral and I said, oh, I gotta take that stalactite. But you can still see some of the correlettes in there. It's a fossilized specimen. If you've ever been down to the Oregon caves or the Shasta caves, all that used to be underwater. It used to be a coral reef. And then through plate tectonics, it was shoved up, became a mountain. These corals and clams and all the shells that you find in the ocean just create layers and layers and layers from thousands or millions of years of buildup. And then you put it up through plate tectonics, becomes a mountain. You have water raining down on it. It washes out, creates holes, and then starts creating stalactites. So stalactites are illegal to collect. The only way you can get them legally is through an estate sale. There are some other examples. I've got one from a lime quarry in England. The tractor driver picked one before he crushed it. It's another example of a stalactite. Came with a collection that I bought when I first got into the industry. This is a stalactite. It's made out of salt. It comes from Cyril's Lake, and we're going to give you another example of that. It comes from a different lake, but it's down near Mojave Desert in Southern California. So same kind of principle. This is salt, same stuff you have on your table. And you may have noticed in the winter where the salt just kind of sticks together is because it absorbs moisture, and then it changes its crystalline structure as it releases and absorbs that moisture. So over time, this has become a different blob over many, many years. This has got a lot of different names. It's Bertrandite. Beryllium is the element that is fluorescent. And I heard Tiffany stone is the third one. Sometimes dealers will change the name thinking they're selling you something different. This is a fossil sponge. It comes in a sliced version. I'm not going to show you that. There's that petrified wood, the limb cast I told you about from Congleton Hollow. This one's green and it only works under the shortwave. Got a great zircon from Malawi, a hanksite that's from Cyril's Lake as well. And Bob, I'm going to turn it
Okay,
over
well,
to
let's
you.
just continue on with lakes. So there's the lake near Mojave that I was talking about is Salton Lake, way down there in the southern part of California. And it's a geyser-based, there's a lot of
They were drilling a well.
We're drilling a well, and the well exploded, if you will. It just made a geyser out of it. And there was limbs and trees and brush around that area.
Dragonflies.
And dragonflies were on the twigs, and the twigs collected the halite that was spraying up in the air, and over time it just evaporated and created a crust around the twigs. And so this is a brilliant specimen. It's just so bright, and that's halite from Salton Lake. It's kind of a neat shape too. It's perfect in that regard. Next door, Jacob Linder has a large display of rocks and minerals. And I went over there this morning to introduce myself, and we talked a little bit. And I'm Facebook friends with the guy. And he says, "Look, I've got this rock." And he says, "You can have it." And let's see, where's the long way?
Fuchsite and ruby. Ruby and fuchsite.
Yeah, there we go. The long way is really, really bright red. Actually, why don't I do it this way? You can see a little better. Get this light on it. Isn't that beautiful? And he's selling me, he said 40, 50 bucks, something like that. I don't know, maybe you can talk him down. But it really is beautiful, beautiful. And it's from India, like he said. Okay. Talk a little bit about, see what time it is, talk a little bit about the collector value of different minerals and rocks. To a collector that wants to have lots of colors in the mineral set specimen that they buy, this might be an example of that. Here's black, orange from calcite, green from willemite, probably some esperite in there, hardisonite. There's just all kinds of minerals in here. This came from a place called Sterling Hill, or Franklin, New Jersey. And that place is just an amazing place. We'll talk a little bit more about that. But the value of this mineral, or this rock, if you will, is probably 100, 200 bucks or more to a collector, maybe even more than that. The more colors, the more the value to the collector. Another way of value is brilliance. How bright is this particular mineral? Why am I holding this again? I can't remember.
Andersonite.
Andersonite. See how bright that is? Just fluoresces immensely bright. As a matter of fact, on the table here, there's residue that's just fluorescing as I look at it. Another way of, for me, this is a piece I purchased. This is smithonite. Where is it? That isn't it. Where's my, oh, here it is. This particular side has conchoidal shapes, and it's got little mirrors in it. When I put a regular white light on it, it just radiates all kinds of little kind of diamond-like colors. But it's also fluorescent. Smithonite fluorescent, really cool. Kind of a peach ruby color. So, but the side that's conchoidal doesn't. So you can have a collection that works both in the daylight and in the fluorescent minerals. One of the things that I did was collect some material in a mine. There was an old abandoned gold mine down in Arizona, Benson, Arizona, and we were going for scheelite and chlorophyte. Chlorophyte is a derivative of fluorite, and it has a really brilliant, long-lasting phosphorescence properties to it. But the scheelite, there's a story I'd quickly tell about World War II. Scheelite is a tungsten ore used to harden gun barrels, and our war machine in World War II was running low on supplies of that ore. China shut it off, and Asia, wherever the markets were coming from. They didn't know where it was in the United States of any quantities. And ultraviolet lights just are coming on the scene. They were huge, back of a Jeep in order to carry them around for portability. And they knew, the geochemists knew that the ore come up with the same principles as gold. You have these gold veins, the hot fluids bring the gold up, the quartz up, and the scheelite ore comes up in the same place as gold does. So they went out to abandoned gold mines, and you got all this roughage, material that they rejected, the tailings, if you will. Brought the Jeep up there, shined the light on it, and this thing just lit up. The ground just lit up. There was scheelite ore everywhere. And so the United States has got massive deposits of scheelite. You can see the little white crystals here. But if you look at this rock by itself, it would just look like a rock. You wouldn't see the scheelite. Okay, so I think I covered that. One of the things that this rock has been cut flat, and it could actually be a foundation from New Jersey. The Sterling Hill complex, where this rock that I showed you had all these different colors in it, the basement material that was an old zinc mine, but the minerals in that zinc mine were developed over several 100 million years. It was when the United States and the African continent were together, and then we created the Atlantic Ocean, and in that process, the New Jersey shoreline was way down underwater. There were a whole bunch of dead creatures dying in the seabeds, and so you got a lot of calcium, calcite being deposited. Then the eruptions of lava and the plate tectonics squeezing things in metamorphics, you get this big mixer going, and all these rocks and minerals are being mixed together as the continents drift apart. And then the zinc material comes up through some veins, and so they go mine the zinc mines. And so the tailings from the zinc mine are laying all over the place, and the people living there said, well, I'm going to use this material that's already broken up, and I'll make cement out of it. So they were selling it. So their house, becomes, the basement part of their house becomes a really brilliant thing. And what's really cool about it is that there's like 90 different minerals that are fluorescent in that area. And it's just really, really bright when it fluoresces. And here's kind of what it would look like in your basement if you turned lights on. So the orange is calcite, the hardizonite is here, franklinite is here, the black speck, willenite. I don't know, there's a bunch of different minerals in there. And it's just an incredible place. It's on my bucket list for fluorescent files people. They have a museum where the hillside up higher than this ceiling has a UV light shining on it. So the entire hill illuminates like this. And then you go in the mine and they got lights everywhere, and this whole inside lights up. Just an incredible place. If you're into fluorescent minerals, big time, take a trip to New Jersey and see the Sterling Hill Museum.
I remembered a couple things I missed there earlier.
Yeah, let's do
you
that.
Want to do your tree too?
Oh, do the tree, but do the
okay.
bullfrog thing, or your.
This is the reason that you wear sunscreen. It blocks out the light. All right. The other one was, if you've ever seen something dead in the water, it'll sometimes grow in this furry little sand bacteria on it. And if you get, it rains, the water starts moving. So as it's dying, it's giving off carbon dioxide. The carbon dioxide acts as a glue, so it's rolling in the mud, and the carbon dioxide's kind of fusing it together for a while. You get more water pushing it along, and it gets bigger and bigger until the water just can't move it anymore. In this particular instance, the water stopped. You've got a plane covered with these cannonballs, if you would. And then the sun baked the cannonballs, and they cracked. And the more time, water brings in more sand, covers up the cannonballs, and the water percolates down through all that material, fills in the cracks with calcite, and you get a septarian nodule. So this is the same thing as that cowrie shell and a lot of the shells. Not all septarian nodules are fluorescent. You got to have a light to find it.
Okay, and we have a club member that created some little small cabochons and had wire wrapping skills. And I'm going to put long wave on it right now. Here's the fluorite is blue, and there's some chalcedony on the bottom that's green. And when I put my shortwave portable lamp on it, here, let's see if I can turn it on without dropping it. There we go.
Oh
Now we see this thing has other colors in it. Calcite is orange now. The fluorite's blue. But it's kind of a cool little display.
All right, got one more thing here for you. This is the phosphorescence, and this is the best phosphorescent display that I've ever seen. It's because we're controlling the white light. I try to do this in regional and national shows. It's just not the same thing. So the watch in the center, and
Everybody get their photograph that they
yeah,
want
this
now?
is the radiating that one, the radiating willemite. It's one of the best.
Okay, you're gonna turn the lights on.
Wait.
Whoa. Quick.
Yes.
All right. Are y'all good?
No,
Almost.
no, wait, just a minute.
All right, here we go.
I
want that light on.
And there's phosphorescence.
Wow.
And you can see how much light that exit sign is filling in the room. It really has to be a dark room to really get the full
I was
effect.
surprised how much the phones do too.
Yeah, the phones light up too.
Yeah. That's that radiating willemite still going.
Okay, so any questions? We're gonna turn the lights on and bring in the next crew. So we have to exit and bring in the next
I
team.
appreciate y'all coming today. I hope you enjoyed the show and have a wonderful day.